All right, so tomorrow we got the Kombucha Lab to do. So just a few things to remember. I needed to remind you guys also about the gravimetric analysis lab that I've turned back to you. If you had a calculation error, and I tried to mark those carefully, so make sure you go back in your lab and look. I think most of you have done that. I need to get corrected values for you so I can get accuracy and precision scores out. So get those to me as soon as you can. If you're not sure how to do something, ask. But I do want to get those numbers soon so I can get accuracy and precision scores for the whole class back out. So obviously for the ones who didn't make a mistake there, I've got numbers, so that's fine, but I just need to get the numbers from everybody else. So there are, I think, 5 or 6 people who probably didn't get the calculations totally correct. So make sure you check that and get those to me, preferably by tomorrow. All right, so as far as getting ready for the Kombucha Lab goes, couple things. It's probably worthwhile when you go through the procedure that I posted on it. I think there's a link to a video in there from Dr. Kagris where he shows how to basically set the apparatus up and how to use it. It's probably worth looking at that just because it'll save you probably a few minutes when you get to lab. So you kind of know what you're looking at and what you need to do. And the second thing is make sure, like I need to remind you because you guys always do, bring your handheld communication device with you. So your cell phone or whatever you use. You can use a laptop as well or a tablet. But basically you have to download an app from Vernier, which basically allows for data acquisition. So again, just to save some time, try to download that app before you come to lab. It doesn't take more than 30 seconds to do, but it makes sense to download it, maybe open it, see what it looks like, play around with it a little bit. And that's what's going to connect to the sensor and control it and also allow you to take data from the sensor. So it's really neat. It's a little Bluetooth unit. So it actually communicates via Bluetooth between your phone or your laptop or your tablet and the actual sensor itself. So it actually works really well. I think those are really the only things to think about. I will have, by the time you get there, a standard solution made, a stock solution of, I think, 5% by volume ethanol. And then what we're going to do is by laboratory bench, you're going to make a series of standards and then share them around the bench. So there should be plenty. We'll make up enough so that everybody has some. And then I'll get the kombucha back out. And I'm planning on using the same kombucha we've been using. I've just been freezing it between weeks. So that way you can get an idea of kind of what the whole picture looks like on your kombucha that you've been using. All right, any immediate questions about that before we hop in? I think it's going to be a pretty good lab. I mean, we've kind of done this to death outside of the lab, so we kind of know how it works. And it's a nice little lab. Everybody good?
Real quick question about the alcohol dilution. I saw it said use the normal dilution equation, but since we're not taking a dissolved solvent, since we're using alcohol, which isn't is not a ideal solution in an aqueous solution, should we recognize that maybe it's not a linear curve, the dilution, or is it a linear curve?
Actually, it is. By the time you set up a standard, Dr. Kagris and I have gone back and forth about this, but yeah, if you actually make up your stock solution as 5% as a volume to volume solution, you're just doing regular dilutions at that point, and that's good enough. So you can go ahead and use your M1, V1, M2, V2. It works perfectly the same way.
Okay, thank you.
Yeah. And that's actually how we do it in practice too. So, we looked at how people actually make standard curves in the industry, and that's how you do it. So I don't think we're doing anything we shouldn't be doing there. All right, so let me go ahead and do a share content here. Good question though. Okay, so let me hop over to my notes. All right, so what do we got? We got quant notes. Today's what, the 31st? No, 29th. I'm getting ahead of myself. All right, so we're getting to the end of March. That's a good thing, which means the weather's going to be warming up. And I feel like we should be getting into near the end of the semester, but yeah, we're not. But that's okay. We'll be fine. All right, so again, we're dealing with the Kombucha Lab here. So what's our goal? Well, our goal is to measure the amount of ethyl alcohol in a kombucha sample. Okay, so our analyte in this case, which is what we're looking for, is going to be that. It's ethyl alcohol. That's the kind that you drink when you're legally of age to do so, I hope. And that has the formula of CH3CH2OH. And sometimes we actually represent it as ETOH as just sort of a shortcut. So that's probably what I'll be doing throughout. But keep in mind that, you know, it's got a formula and a molar mass and all that normal stuff. Now, as I mentioned, ethyl alcohol is the kind of alcohol that you would find in alcoholic beverages such as beer or wine or various liquors and things like that. So obviously it's something that if a drink or a beverage contains it, we have to keep track of how much is in there. Now, when we brew kombucha, it turns out that because of the fermentation process, and kombucha, just like beer, is a fermented beverage, okay, there's going to be some natural alcohol occurring there. The difference is in the production of kombucha, what ends up happening is the yeast make the alcohol, but then the alcohol gets consumed by the bacteria that actually also inhabit the kombucha as part of the live beverage. Okay, that's the probiotic part. So as a result, we wouldn't expect to see alcohol contents as high as we would see in a normal fermented beverage such as beer. Beer is typically anywhere from maybe 4.5 to maybe 8% alcohol by volume. Kombucha is generally going to be considerably less than that. But here's the problem. If I want to produce and sell kombucha, okay, I want to be able to classify it as a non-alcoholic beverage, okay? Because otherwise, if I classify it as an alcoholic beverage, I have to have a state license to sell it. Different taxation rules apply to it, okay? And also, it limits the age groups to whom I can sell it. So if I have an alcoholic beverage, you can't buy it unless you're 21 years or older in Pennsylvania, for example. So it makes sense that if I'm selling and marketing and producing kombucha and I want to legally sell it, I got to make sure it's non-alcoholic. Okay, so that's really what we're worried about. It's a non-alcoholic beverage. So what do I mean by non-alcoholic? Because I just mentioned to you that there's some naturally occurring alcohol in any kombucha that we make, right? Because it's part of a fermentation process. So what non-alcoholic means is that in the beverage, I'm going to have less than 0.5% ethanol by volume. Okay, so we need to kind of look at these units of measure. It's a volume percent that we're after. Okay, so in a sense, a volume percent's a lot like a mass percent. That's one we use way back in bonding, and you still maybe use it from time to time in dynamics. So if you use, for example, mass percent as an example, what would volume percent actually be? How would we actually define it as a concentration unit? What's it equal to? Well, go ahead.
Okay, sorry. I thought you were asking a question. It
Yeah,
would be
I was. Go ahead.
milliliters of solute divided by total milliliters of solution.
Okay, yeah, we can say that. So milliliters of ethanol, ETOH, it could be any volume unit, but milliliters are convenient to use, divided by the total milliliters of solution, right? And then to turn it into a percent, we multiply it by 100. So you can see how it looks like a mass percent, only we're using volumes instead of masses. All right. Now, there's another way we can take this. So when we really start to talk about alcoholic beverages with higher alcohol contents, we can actually even convert that to proof if we want to. Okay. So that's another way it can sometimes be looked at. We don't usually use proof for things like beer, wine, or kombucha because they're very low alcohol content. But if we get to the point where we're talking about various distilled beverages such as liquors and spirits, what proof turns out to be is twice the percent by volume. Okay, so it's 2 times the volume to volume percent. Okay, so for example, if you know, I have a rum sample, and that rum sample is 40% ethanol by volume, it's 80 proof. Okay, so in the case of kombucha, if my kombucha is 0.5% volume to volume as a percent, then the proof of the kombucha would equal to 1. So we'd say it's 1 proof. Okay, so I just took the volume percent and multiplied it by 2. All right, so that's just another way that we see that alcohol can be quantitated and reported out in these kinds of beverages. But again, for really low alcohol, things like kombucha, we don't bother with proof. We usually just report out as a percent by volume. All right, everybody okay with that so far? So how are we going to do it? In other words, what does the experiment look like? So we want to think a little bit about the experimental design. Well, if you look at it, we're going to generate a standard curve, right? Have we used a standard curve in Quant yet? I'm not so sure we have. All right, but the idea here is that I can take a series of standard solutions of known concentration of, say, ethanol, and I can measure the amount of ethanol in each one of those standards. And I can generate a mathematical relationship between my detector response, whatever that is for the instrument I'm using to make the measurement, and the concentration. All right, so once I have that relationship for a series of standards of known concentration, and I have a mathematical relationship such as a straight line, which is how we normally do it, although that won't apply in this case, then I can utilize that equation for the straight line to determine the concentration for an unknown as long as it falls somewhere on the curve. Okay, so in other words, I would get a detector response for the unknown. I can plug that in for my Y value in my equation. I can solve for X, which is concentration, and boom, I'm there. Okay, so that's how we do it. And we use standard curves also in other labs that we do in Quant. I can think of one specific one that we end up using a standard curve in as well when we do spectroscopy. But to generate my standard curve, what I'm actually going to be looking at is essentially a detector response. So I need a detector response. So what's the detector responding to? Well, in our case, the detector response is going to be the vapor pressure of ethanol above the solution. And that makes sense. Think back to your dynamics, right? When you talk about solutions and vapor pressure. As long as a solution has one or more volatile components associated with it, there will be a measurable vapor pressure there. Okay, so in other words, in our case, we have ethanol molecules in the gaseous phase above the solution. Now, you also remember from your dynamics that the concentration of the ethanol vapor or of ethanol in the vapor is a function of the concentration of the ethanol in the solution, right? Think back to Raoult's law. All right, and we'll get into that in a little bit. But the idea here is that as the mole fraction or concentration of the ethanol in the solution increases, the vapor pressure of the ethanol above the solution should also increase in a linear fashion. Okay, so that's what we're actually measuring. So if I can actually get a measure in terms of detector counts or response that scales with the vapor pressure of the ethanol above the solution, then that should tell me something about the concentration of the ethanol in the liquid solution. And that's ultimately what I'm trying to get to. Okay, so does that make sense to everybody? I'm measuring essentially in an indirect way the vapor pressure of the ethanol above the solution. That's what I want to do. And then I want to relate that back to the ethanol concentration in the liquid solution. So how does the sensor do this? How does the sensor actually work? Okay, so the sensor itself, so I can get a response from it, is based on what we call FET technology. Okay, and FET stands for field effect transistor. And we study this a lot more, for example, in analytical chemistry, which you guys will take. And what I'm going to try to do is essentially describe this in a very, very simplified manner, okay? So essentially what I've got is a sensing surface. And what's going to happen is ethanol molecules in the vapor phase can adsorb to the sensor surface. All right. And this, of course, has to be a reversible process. I can't let them actually adsorb, and then if they don't come off, then I can't reuse the sensor, right? So they can adsorb, and then if I take the ethanol away, they'll desorb again. And that'll sort of reset the sensor, if you will. Okay, so that's the idea. This has to be a reversible process. So in other words, if I think about this as a sensor surface here, and I've got an ethanol molecule here, the ethanol molecule can work its way down to the surface, and then it can work its way back off again, okay? But as it turns out then, if I have a higher concentration of gas phase ethanol molecules, right, then the likelihood of adsorption to the surface increases. Now, why does this matter? Well, it turns out that when the molecules adsorb to the surface, the effect of this is that's going to increase or decrease, in our case, decrease the conductivity of the actual sensor. In other words, how well does it conduct electricity? Okay, so if I can somehow measure the conductivity of the sensor, then that tells me to some degree how many ethanol particles are actually adsorbed to the sensor surface. And that in turn is a function of the composition of the vapor, which in turn is going to be dependent upon the concentration of the ethanol in the solution. Okay, does that kind of make sense to folks? So here's what the thing would actually kind of sort of look like. So we're going to do a little electronics here. So I'm going to have a voltage source. This is kind of like a battery here. So DC voltage source, okay? And I'm going to represent the sensor surface as a simple resistor, okay? So this would be a resistor down here. And this is a really, really, really simple circuit. So if I have a resistor here and I have a voltage source, okay, what ends up happening is the voltage source is what pushes current through the circuit, right? So think about, I remember being in the 3rd grade, right? And everybody thought I was brilliant because I knew how to wire up a circuit, but it was a really simple circuit. They just kind of gave us some wire, a light bulb, and a switch, and a battery. And, you know, you had to figure out, okay, how do I put all this together and make the light bulb light up? So obviously you have to hook it up into a closed loop, right? And then you have to close the switch. And once the battery is in contact with the circuit and the light bulb lights up. Not rocket science here, guys, even to a 3rd grader. Although, you know, everybody's like, wow, he's so smart. It's like, yeah, you just got to close the circuit. So that's essentially what we're doing here. So the resistor here is the sensor surface. Okay. So when I talk about this, as I mentioned, current will flow through the circuit as long as I have a closed loop here. What's current? Current is just the flow of charge. So we typically think about it as electrons moving through a wire, through the resistor, and then back around to the opposite pole of the battery. So how do I relate all these things? Well, all of these things get related by something called Ohm's law. And what Ohm's law says is that the voltage is equal to the product of the current, which is I, times the resistance of the circuit. If I only have one resistor in there, that's easy. It's just the value of the resistance of the resistor. Okay, so the nice thing about this is I could then solve this thing for I, and if I do that, it's the voltage, which is of course a constant because it's supplied by the battery. That doesn't change. If I have a 12-volt battery there, for example, I'm going to have 12 volts constant over R. And R, of course, is the value of the resistance of the resistor. Now, in a regular circuit, that would be a normal resistor, maybe that has a value in ohms of resistance. So it might be a 100 ohm resistor or a 10,000 ohm resistor or whatever. But in our case, the resistor is actually the sensor surface. Okay? And what did I just say about the sensor surface? Does it have a constant resistance or variable resistance?
It's variable depending on the absorbed ethanol.
Yeah, so basically I'm controlling the resistance of the resistor based on how much ethanol adsorbs to it in the vapor phase. So the more ethanol that adsorbs to it, the more resistive it becomes. So let's say I is the variable we're measuring. So I here could be, for example, the detector response or the sensor response. Okay, what would happen to the current? So if I have a low ethanol concentration in solution, I don't have a lot of vapor, so I'd have less absorption. So what would I be, big or small? Relatively speaking. If R is small, what happens to I? Does it get bigger or smaller?
It would get bigger.
Yeah, I is big if I don't have a lot of absorption. But what if I have a high ethanol concentration and a high concentration of ethanol in the vapor? I get more absorption. So now what happens is R gets bigger. So what happens to I?
Gets smaller.
I get smaller. So we could actually look at those sort of limiting cases down here. So this could be my surface here. And let's just say I have only a few ethanol molecules absorbed. And then over here, same surface. Now I have a lot more ethanol molecules absorbed to it. Okay. So this might, for example, be a small r. So let's just give it a value. Let's say it's 1 ohm. Ohm, by the way, is the omega there. And ohm, of course, is the measure of resistance. Okay. Over here, I might have a large resistance. So let's say it's something like 100 ohms. Okay, because I have more stuff absorbed. So what would happen? Well, I can solve this. I is equal to V over R. And let's just say my voltage is 1 volt. Keep the math easy. Divided by 1 ohm. I get 1 ampere. And an amp is a volt over an ohm. Another way of thinking about it is the amount of charge that moves through the circuit per unit time. Okay, so it could also be given as coulombs per second because coulombs is my measure of charge. All right, the other option is I could have I is equal to V over R here. My V is still set at 1 volt. That's what the battery gives me, but now I'm going to divide by 100 ohms. And what do I get? I get 0.01 amps. Okay, that should be an A there. So obviously, if my response here is in terms of current, I should be able to generate a standard curve, which I can then relate back to the concentration of the ethanol in the vapor, and hence the concentration of the ethanol in the solution. All right, so that's essentially in a very, very simple way how the sensor itself actually works. Okay, now I've oversimplified things tremendously here. It's not just a simple resistor, but that's just a simple way to model it for us so we can kind of understand. It's really a transistor, which is different from a resistor, but you know, the same kind of argument will hold. All right, questions from you guys about this? Does it make sense?
Yep, I think so.
All right, good. Because I'm introducing some new terminology and stuff here. This is kind of like baby level analytic. Okay, so this is good, but it's good that we're kind of introducing these concepts early on. So when we do see them in analytic, by the way, this is the very first stuff we do in that course. So, you know, you'll be able to say, yeah, I saw that once before. But now let's go back to the concept of vapor pressure. So now we know what we're actually measuring, but I want to talk about vapor pressure. And this goes back to stuff you learned earlier in the semester in dynamics. So remember, we always say that quant is kind of dynamics on its head. So in other words, in this case, we're going to kind of go back and review some stuff that you talked about, maybe a month ago in dynamics when you were dealing with solutions and intermolecular interactions and those kinds of things. So when we talk about vapor pressure, which is really kind of what we're measuring here, let's just sort of simplify what we've got in kombucha. Now, I'm going to way oversimplify here. I'm going to say that kombucha is a very simple mixture of ethanol and water. Now, it's really a much more complex mixture than that, right? There's all kinds of other stuff dissolved in kombucha. And there's also other volatile components associated with kombucha. Ethanol is not the only one, okay? So for example, kombucha, as you guys know, is carbonated. So we've got carbon dioxide gas that exists in the vapor above it. Also, there's acetic acid in there. And acetic acid has some volatility associated with it when you dissolve it in aqueous solution. And you know that because when you pop open a bottle of vinegar, you can smell it, right? You can smell the acetic acid. So it has a vapor pressure too. But for the most part, we're just going to consider kombucha to be simply ethanol dissolved in water. Again, just to keep things simple. So let's just compare these two things. Let's look at boiling points. The boiling point of ethanol is 78 degrees Celsius. That's the normal boiling point of it at sea level. The boiling point of water, you guys also know, is 100 degrees Celsius. And I also just happened to look up the delta H of vaporization for this. That's a standard, sorry, that should be a delta H, not a delta V. And that's a standard delta H of vaporization. I can do that for both. It's an enthalpy of vaporization. And for ethanol, that turns out to be 38.6 kilojoules per mole. And for water, that turns out to be 44.0 kilojoules per mole. Now, we all know what boiling point corresponds to, right? But what is a delta H of vaporization? So in other words, I give you a number. I tell you that the delta H of vaporization of water is 44.0 kilojoules per mole. What's that telling me? What does that physically mean?
Heat needed to change from a liquid to vapor stage.
Yeah, that's exactly right. So it's the amount of heat I have to put into a sample of water to convert 1 mole of it from the liquid phase to the vapor phase at standard temperature and pressure, right? So that's 1 atmosphere and 298 Kelvin. So that's what it means. Now, what do these things tell us? Well, they tell us something about intermolecular interactions, don't they? So if you take a look at the boiling point of ethanol and the delta H of vaporization of ethanol versus water, what does that tell you about the intermolecular interactions of ethanol between ethanol and water?
Water has stronger intermolecular interactions between itself.
Yeah, certainly stronger interactions. And that's reflected in both of those numbers, right? It takes more heat to generate a mole of vapor in the case of water than it does in the case of ethanol at the same temperature and pressure. Also, it reflects in the boiling point as well, right? I have to go to a higher temperature to get water to boil than I have to get ethanol to boil. Now, why does water have stronger intermolecular interactions than ethanol? So why is water stronger?
Is it because of the H bonds that it contains?
Yeah, so water, remember, looks like this. Okay. Now remember, ethanol looks like this. I'm just going to write it out. I'm not going to actually show you the whole formula. Okay. Yeah, we'll just use dashes here as well. I like dashes rather than dots. So can both of them hydrogen bond?
Actually, yes, there is a hydrogen bond with a hydroxide.
Yeah, both of them have a hydroxide in it. So both of them can hydrogen bond, right? But why would water hydrogen bond better than ethanol?
We don't have that large non-polar part being in the way. We can make 2 hydrogen bonds since we have 2 hydrogens per oxygen rather than 1 hydrogen per oxygen.
Yeah, that's exactly right. I mean, that's the best case scenario is basically with water per molecule, I can make 2 hydrogen bonds, right? Water to water, but over here, I can really only make 1 hydrogen bond between one ethanol and its neighboring ethanol. That's the best I can really do. Okay, so it makes sense that even though hydrogen bonding is present, we know hydrogen bonding is like the strongest kind of bonding that I can have outside of ionic, right? Ion to ion. You know, if you can make 2 of them per molecule, you're going to have a stronger interaction than if you can only make 1 of them per molecule. Makes sense to everybody? And not that that's terribly relevant, but it just lets us kind of go back and review some stuff that you guys already learned in dynamics, which is always a good thing to do. Okay, so that's what I've got. Now, what if I want to, again, make this solution of ethanol and water? So kombucha, as I mentioned, is a solution of those 2 things. Okay, how do I characterize that solution? Well, one way to do it is I want to define the total pressure above the solution, right? So how would I go about doing that? What does that depend on? What does the total pressure above the solution depend upon? That's probably an easier way to go back and think about it.
Moles of gas.
Well, it's composition, right? I mean, because we're going to assume that, you know, we're working at a constant temperature, right? Because if we're not at a constant temperature, all kinds of funny things happen. Remember the Clausius-Clapeyron equation, right? So if we talk about vapor pressure and temperature, there's an exponential relationship between those 2 things. So obviously we want to keep temperature constant. The other thing we normally would do is say, okay, we'll either put it in a closed system, or if it's an open system, we have a constant atmospheric pressure. Okay, so really when you get down to it, the total pressure depends upon the composition of the solution. In other words, how many volatile components you've got in there and what their relative concentrations are, right? So it really comes down to 2 things. One of them is this, and we'll just use our kombucha as an example. We can use Dalton's law of partial pressures, right? So we can say that the total pressure above the solution has to be the partial pressure of the volatile components, which in our case is just going to be the water and the ethanol, right? But then, can I break that down into some sort of a concentration unit? Yeah, we can, because remember, we have Raoult's law, so that's Dalton's law of partial pressures. And then we have Raoult. Now remember what Raoult says. Raoult says that I can, for each one of these things, define a partial pressure, for example, of the water, as equal to the mole fraction, that's what the chi or the big X here stands for, times the partial, or times the pressure of the water by itself. So that P naught is the vapor pressure of the water. That's just regular water vapor pressure, which you can look up, for example, at a specific pressure and temperature. Okay. Now I can also do the same thing for the ethanol. Turns out that's equal to the mole fraction of the ethanol that I've got in the solution, times again, the vapor pressure of the ethanol by itself. That's what the naught stands for. Okay. So now what we normally do is we just plug these things back into Dalton's law. I'm sure you guys did this in dynamics. I'm not sure every instructor does this. I know I do it. Have you guys seen this before?
Yeah.
Okay, it might depend on who you had. But anyway, what you end up getting is chi of H2O times the pressure of water by itself plus the chi of the ethanol times the pressure of the ethanol by itself. And again, chi here stands for mole fraction. And again, it never hurts to go back and review that. So the chi for the H2O, it's a concentration unit, right? It's equal to the moles of the H2O divided by total moles of solution. So that would be the combination of the moles of the water and the moles of the ethanol, wouldn't it? Because that's what my solution is made up of. Okay, so that's just a quick review of that. So now what we end up doing is generating, to kind of get an idea of how this all depends on composition, we can generate one of these Raoult's law plots. Now, you guys probably remember seeing these, for example, in your textbook, or maybe your professor showed you some of these. So it's kind of one of these things where I can look at, say, the pressure of the ethanol on one side, and I can look at the pressure of the water on the other side. And again, these are vapor pressures we're talking about. And these can be in atmospheres, for example. I think I actually did them in atmospheres. And I can look at that as a function of the composition of the solution. So I can go in terms of mole fraction from 0 to 1 in the case of the ethanol. So that's chi for the ETOH. But I can also look on the axis going from 0 on the right to 1 on the left for my chi for the H2O. Okay, so notice as one gets big, the other one gets small, and as one gets small, the other one gets big. See how I'm working that? So I can kind of look at both of them simultaneously there. So what I did was I defined a temperature. Okay, and I said my temperature at which I'm doing this is going to be the standard 25 degrees Celsius, right? Standard room temperature. I went and looked up what the vapor pressure of water by itself is at 25 degrees Celsius. And water by itself turns out to be 0.03 atmospheres. And I did the same thing for the ethanol. I went and looked up the pressure of ethanol by itself. It's vapor pressure at 25 degrees Celsius. And that's 0.08 atmospheres. Did what you guys would have done. I just went to the internet. Okay. So what we can end up doing is I can look at the ethanol here. If I'm at 0 mole fraction of ethanol, my pressure is going to be 0, right? Because there's none in there. But now as I increase my mole fraction of ethanol from 0 to 1, where 1 would be 100% ethanol, what do? I basically just make a line between 0 and the 0.08. So, if I do this right, I can just kind of make a line that connects those two things that would look something like that. Okay. Then I can make the same argument for the water, right? If I'm starting out with 0 mole fraction on the right, because that's the water, right? And then I go up to a mole fraction of 1, which is pure water. Okay, then my vapor pressure ought to be 0.03 because that's the vapor pressure of pure water. So what I can do now is generate a line that goes again from there up to there. And then if I want the total pressure in solution, what do? I want to know the total pressure above the solution. What do I have to do at any given composition? So in other words, let's just pick a composition right here. So I've got a certain mole fraction of the ethanol, and then I've got a certain mole fraction of water that corresponds to that, right? How would I get the total pressure above the solution? What would I do with those pressures?
Add your 2 Y values.
Yeah,
Your
just add my
pressures.
2 Y values. And it makes sense here. This is a reason I picked this, is because that's where the two cross, so they ought to be the same. So if I add them up, I'll get a point that's maybe somewhere around there, right? So basically what I end up doing, and you can show that's true anywhere along here. I could take my point here and my point here and add them together, and I'll get a point that's maybe about there. So what you can see is that basically what I do is I just tie the two vapor pressures together. And I end up getting something that looks like that. So that's going to be my total pressure. It's just the sum of the two at any given composition. And that just comes from Raoult's law, right? Now, here's the other interesting thing about this. You guys might remember from class that this is what we would see for an ideal solution. Okay. Does anybody remember what we mean by an ideal solution? So we get a nice straight line like that. So that's
a solution where all the interactions between the molecules are equivalent.
Yeah, so basically all the intermolecular interactions cancel out. So what intermolecular interactions do I have to account for? Well, here's what I have to account for. I have to account for the interactions between H2O and H2O. I've also got to account for the intermolecular interactions between ethanol and ethanol. Okay, those are kind of your solvent-solvent ones. And then what's the other kind of interaction I have to account for on the other side of the scorecard?
H2O and ethanol.
You got it. So this is the other one I got to think about. H2O and ETOH. Okay, now if I have an ideal solution, basically those things equal out. All right, so in other words, how do I think about this? I kind of think about it almost in a Hess's law kind of way, where if I'm over on the left-hand side, I've got to break a bunch of water-water interactions, and I got to break a bunch of ethanol-ethanol interactions so I can sort of mix everything back up and make the solution. But then when I form the solution, you know that new hydrogen bonds form between the water and the ethanol, so I get some of that energy back. Okay, so sort of breaking the interactions on the left costs me energy, but forming the new interactions on the right-hand side get me energy back. And if those two things equal out, then I've got an ideal solution. And that's when I get that linear relationship that I just drew up there for my P total. Okay, that's the ideal solution. But in many cases, can we say that those two things are equal to each other? In reality, is that how often is that going to happen?
Not very often.
Probably almost never. Okay. So what ends up happening is you end up getting what's called either a positive deviation from Raoult's law or a negative deviation from Raoult's law. In other words, at any given composition, what's going to happen is the vapor pressure is either going to be higher than expected from our Raoult's law plot for an ideal solution, or it'll be lower than expected. Now, it turns out for the ethanol water mixture, we get a positive deviation. So the way that looks is you end up getting sort of a curve that comes up like this and then comes back down again. So that's what we actually see. We end up getting a positive deviation from Raoult's law. Okay, so what is that telling me? What it's telling me is that at any given composition now, the actual vapor pressure is higher than expected for an ideal solution. Everybody see that? So if I just kind of use my reference point here, go all the way to the top, here's the expected value for an ideal solution, but the actual value we see is higher than that at that same composition. So what is that telling me about the balance of the intermolecular interactions? Okay, which one's winning out in terms of being stronger for a positive deviation? The ones on the left or the ones on the right? Which ones are stronger ultimately if I get a positive deviation?
I think that the left side is stronger because even if we introduce a little bit of ethanol, that's gonna make it deviate greater. I think.
Yeah, that's basically exactly right. So what's going to happen is if I have a positive deviation, what it's telling me is that the pressure is higher than expected, right? So what that means is that these interactions over on the left are going to be stronger relative to the ones on the right. Now, what do the weaker interactions on the right tell me? Well, it tells me that when I make the solution, right, those interactions are weaker than we would expect. And if they're weaker than we'd expect, that would contribute to a higher vapor pressure, wouldn't it? Think about the alternative. What if the solution gave you stronger interactions than the individual solvents by themselves? If we have stronger interactions, what effect would that have on the vapor pressure of the solution? Would it go up or go down?
I have a feeling it will go down.
It would go down because it's harder for those molecules to escape the surface, right? Because they're held more tightly. So that's kind of what ends up happening. So ultimately, what our sensor is responding to is Raoult's law, okay? But there's one other little problem that I see here. Okay, what is it that I want my sensor to respond to?
Ethanol only.
Ethanol only. But what have I actually got?
Ethanol and
Ethanol and
H2O.
water.
I got ethanol and water in there. Okay, this is a problem, right? Because now the sensor might respond to something I don't want it to respond to. So what this deals with is this issue of what we call sensor selectivity. So if it turns out that my sensor responds equally to water and ethanol, how am I going to get the ethanol information back out if I don't know something specifically about the water vapor? Well, that would be hard, wouldn't it? So what I want to do is actually build selectivity into the design of the sensor if I can. Okay, and this is something we have to do in analytical chemistry all the time. So the problem is that we don't want to measure the pressure due to the water. We only want the pressure due to the ethanol. Okay, so how might I build selectivity into the sensor? Now think about it. If you read the instructions for the sensor and we're setting the sensor up, there was something we had to do before we used it. Does anybody remember what it is?
The Teflon tape, which I'm assuming is acting as a permeable membrane.
Yeah, we're gonna apply the Teflon tape. Very good. So basically what we have here is a situation where this is the tip of the sensor. Okay, and then there's a gap here. So the sensor surface might be right here. And then what happens is there's a gap here, okay, that kind of protects that. So what I'm going to do is I'm going to put Teflon tape over that gap. Okay, so we can kind of just bind it on there. And it acts kind of like you said as a semi-permeable membrane. Now, by semi-permeable, what we mean here is that some things get through it and other things don't get through it. You learn about that, for example, I think when you're talking about osmosis, right, or osmotic pressure. That's probably the other place where you've seen that term. So if I look at the chemical structure of Teflon, it's a polymer. It's basically a chain of carbons, and then bonded to these carbons in sort of a tetrahedral fashion are fluorines. So each one of these carbons, if I were to look at it, is essentially a carbon bonded to two other carbons, but also bonded to two fluorines. So I'll put an N there because that's repeating in a long chain. Okay, so if you look at this and work it out, and you looked at this in 3 dimensions, we can see that the carbon fluorine bonds are polar. But if we look at the polarity of the whole molecule, what ends up happening?
It's non-polar because you don't have regions of polarity. It's just all polar, so it's
Yeah, so
non-polar.
basically what we have is a situation where sort of the dipole moments end up canceling each other out. So the whole molecule is non-polar. Okay, so what does that mean? If I put a Teflon tape barrier over this thing, what's not going to get in?
The water.
Water. Okay, so as a result of this, H2O gets excluded. Now, as it turns out, yeah, ethanol is a reasonably polar molecule, but it's just non-polar enough that it can make its way through the Teflon barrier. Okay, but water gets excluded out. Okay, so now what am I actually looking at here? What I'm really looking at in terms of the sensor is hopefully just the ethanol vapor. We're excluding the water vapor from it because the water vapor can't penetrate the Teflon barrier. Does that make sense? So now let's think about what our standard curve looks like. We're going to make a standard curve, and it's going to be essentially the sensor response, which is just numbers. What they actually do is they turn it into like actual percents. So ideally with this sensor, they kind of want you just to read off percents by volume minus an external standard curve. But we do the standard curve because we'll get a much better value. So whatever number it gives you, it's just a sensor response. And we're going to look at that as a function of volume percent. of ethanol, okay? And like I said, we're going to generate some standards here. So we could do a 0, 0, which would be just water. That's actually kind of an interesting thing to do. Just measure water by itself and see what the sensor tells you. It's going to be pretty darn close to nothing. And then what's going to happen is you're going to get, and I think it's actually shown there, you're going to get something that isn't quite linear. It's actually polynomial. So if I actually were to fit a curve through this thing, what you're going to get is a second order polynomial fit. Now, why do you think it's not linear? Give me a reason why you don't think you get a linear response out of that, based on what we have talked about here in today's lecture.
Is it because of the interactions between the, I'm not sure what it, was it the ethanol then? Would there be the interactions between them, which wouldn't?
Yeah, actually go back and look at your Raoult's law plot.
Yeah, Chi,
So
right?
chi is concentration, right? Now it's not volume percent, but concentration is concentration is concentration. Whether we're talking about a mole fraction or a volume percent, there's going to be a direct relationship between those, a linear relationship between those concentration units, right? If one goes up, the other one's going up proportionally. Okay. So what do we see there? Well, even though we're actually just looking at the ethanol part, okay, does the deviation go away? No, it doesn't. The deviation doesn't go away. So what we actually probably see, and remember, we're only looking at a very, very narrow range of this curve. So what we're seeing is probably that deviation very slightly building out like this. Okay. So rather than getting a linear response over that very small portion of the curve down at the low concentrations where we're at, what we're probably seeing is a polynomial fit where linear would probably look something like this because of that positive deviation as the mole fraction of the ethanol in the solution and hence in the vapor is increasing. Does that kind of make sense? That's kind of my hand waving argument as to why we're probably not seeing a linear response. Now, it could also be a function of just the mechanism by which the ethanol molecules bind to the surface of the sensor too, or it could be a combination of those two things. But to me, that kind of sort of makes sense. So what do you guys think? Does it kind of make sense now in terms of what we're doing?
Yeah, a lot more sense. It really does.
Good, good. It's always nice to go and do an experiment, kind of understanding what the experiment's about and kind of what the basic chemical know-how behind the experiment is. So now you can sort of think about when you do the experiment, why the sensor might be responding the way that it is. All right, well, good. I hope that clarified some things. So any other questions? And again, what's due tomorrow? It's the notebook, right? From the first Kombucha Lab. So it's your pH data, it's your titration data, your first derivative plot, and then I think there's like a little post-lab question about calculating a Ka in there. Is that right?
Sounds about right.
Hey, by the way, have any of you done your curves yet? How do your titration curves look? Do you get the waterfall plot and all that? I haven't seen any yet.
Yeah, it turns out pretty good.
Okay, that's good to know. And hopefully it'll generate a nice first derivative plot for you too. Because like I said, I haven't seen these kombucha samples, so I don't know how they're going to turn out. This is all brand new to us, so I'm just hoping for the best. All right, I've kept you guys a little long today. So any other questions? Everybody good? All right, if I think anything, I will let you know by email, but I think I caught most of it. So I'll go ahead and stop recording and stop sharing. And if everybody's good,